So this is those stylized slides I showed yesterday, outlining the algorithm used by STSim, or state and transition simulation models. And so we talked about here in the examples so far, all of our rates, whether they be probabilities or targets, have been more or less fixed in time. But there's this idea now that we might want to make the probabilities and or the targets vary over time to reflect the kind of variability that we know is there in our real system. And so that's what we're going to do in this exercise is we're going to look at how to address and incorporate that kind of variability in time into our models. Next exercise we'll do it spatially. And so we'll see that there's a couple ways you can do this, but one is to shift these probabilities up and down over time using what we call multipliers. You can also shift the targets up and down using multipliers. And then we also have another way, it's kind of connected, where we can introduce distributions for these values. So we can plug in distributions for either the probabilities or the targets, and then sample from those distributions over time to get variability as well. So we can kind of mix those two. So those are the two basic levers we're going to look at in this exercise. The exercise we'll look at, I was just going to introduce the landscape a bit more. So this is the landscape that you worked with in exercise 3, and I think you'll be working with the rest of today. It's actually this forest. It's in my province, home province, Ontario. It's sort of, I think the whole forest here, we're working on this Trout Lake forest in purple. I think it's probably 800,000 hectares in size, roughly, so close to 1 million hectares in size. And if I just bring up this other slideshow, is it going to behave? No, it's not.
No, Colin, would be more interesting if it were in Quebec than Ontario, but I'll let that go by.
Why would you say that? Oops. Oh, actually, I gotta get to the right slide. That would help. Oh, I want to go through all this stuff. Sorry about this. Here we go. This is the slide I wanted. So let's change the view now. Oh, that's not what I. Crap, oh, it's good. That'll do for now. So this is that forest that we're looking at. I think in your data set you're looking at 1/10 of this forest. So it's some portion of this that we cut out so that the run times are bigger. But in the original model, just to give you an idea, we're running at 250-meter resolution. So those cells were 6¼ hectares. I think in your working exercises it says acres, but it's actually hectares. And we're dealing with models of succession, wildfire, and harvest that you've seen already. In the original model, we used 12 states, just to give you a sense. So there's more diversity in species composition. We simplified that down to 3 states just for the course to make it simpler. And the thing that we used in this then is, you'll see this, that we have this fire record for this area that we're going to be working with over the next 2 exercises. That's kind of all I wanted to show you on that. And so that's just an introduction, so you understand the context a bit more. The last thing I'll just show you is the data set you're going to be working with in this exercise. The exercise actually goes through it a bit, but I'll just show it to you anyway. So this is the fire history for that area. The area burned. We show it in acres here. Again, I don't know if it's acres or hectares, doesn't really matter. But you get this pattern of burn areas where you get the odd really high year and many years with no fire. And so what we want to try and do in this exercise is reproduce this pattern in your model of variability in fire. And we've kind of, to just summarize, this pattern. This is the original data set that's plotted there, 30 years of fire, area burned. And we can summarize this in a couple different ways. The first is that we can normalize this data set so that we can look at the mean. The mean area burned is 1,900 acres over this 30-year period. And so if we take the actual area in each year divided by the mean, call this the normalized area, then in 84 there was 4 times the mean in fire. In 1998 there was 10 times the mean. Many years there was 0 times the mean, and so on. So this is the number. We're actually going to be using this, and you'll see in the exercise why. And this is the plot of the distribution, the frequency distribution of these values. So you can see here that there are 10 out of the 30 years that have a count, normalized area burned of 0. There's quite a few years, again, 15, half of them that are, 0 to 1 in terms of the mean. So that's why that's the mean. And then there's just a few years with more than the mean in fire, spread out like this. Does that make sense? Any questions about that? So you're going to take that now in this exercise and go to it. You'll just be working to try and reproduce that fire history in a bunch of different ways. We had this first scenario we were looking at, right, where we were just modeling, if we just look at it, the fire, let's just bring up a chart. We're looking at the amount of fire in our landscape, and we were looking over the historical period up to 2013, and we saw that we were able to reproduce exactly the pattern of fire that was observed in the historical period, which is somewhat useful, but and sometimes we do retrospective simulations, particularly when we're trying to fit or calibrate our model and make sure that it's producing the results that we expect. We can run it over a historical period, and so this kind of thing is done quite often when we're doing those retrospective simulations. But the challenge we then had was trying to take this pattern of variability in fire that was observed historically, and then somehow characterize it in a way that we could make projections into the future. So skipping over a couple of the steps in between there, we were just getting used to using multipliers. We got to this scenario here that you saw where we were characterizing the future fire based on the temporal distribution of fire years that we saw in the historical period. And so we use this distribution feature, right? Actually, I should just bring this open, go here, distributions, and basically what we're doing in here is putting in a frequency distribution of how often we expect our fire to shift up and down over time relative to the mean amount of fire we expect. So these were all the normalized values. And so what we would end up with is the model was set up with some base fire probabilities that were over in here for the fire, and these were still in play on average, but the historical pattern of area burned was used to shift that amount of fire up and down in the same proportions that we saw in the historical record. So we weren't actually reproducing the area burned per se, we were reproducing the variability in area burned that we observed in our time record and applied that to these probabilities that were derived potentially from some other source. And again, we could have actually created the multipliers to represent the true probabilities rather than if we had some data that told us the probability. but we didn't really have that. We had area burned, which is just a surrogate for the burn probabilities. And so that's why we didn't use them directly to estimate fire return intervals and thus the variability in the true probabilities. Although in other projects, we have tried to do that kind of thing. It just takes a bit more data to do it. Does that make some sense as to what we're trying to do? Any questions about that? The sort of intent of that part of the exercise? And so if we did that, let's just take this off. We could get, let's just look at, this is the baseline probability. So this is with no variability, and that's that same baseline probability with the variability added. And so if we look at our fire then, what we'll see is that if we look at it over all 6 Monte Carlos, we see that we can sort of see this trend that we can't confirm it for sure, but it looks like the area burned into the future on average is the same under both scenarios, just one has variability. And this is one of the challenges you see now running too few Monte Carlos. Because this simulation has so many years, so much range and variability, and so many years, in this case with no area burned, that when we only run 6 Monte Carlos, we're not really getting a very accurate estimate of the uncertainty in each year, because just by chance, in 2022, all 6 sampled values were near 0 in terms of the total area burned. So what I did is I went ahead and reran that same scenario with 100 Monte Carlos, just so you could see the difference. And that's what you get in green. Now you can see that we get a clear estimate of the uncertainty, and this is the uncertainty over all 100 Monte Carlos. And as you would expect, there's no one year that shows more or less uncertainty than the others. And if we tick off the red one there, actually the colors have changed. This is 100 Monte Carlos. Now you see that the mean area burned with and without the variability is now converging to the same values. We're just introducing this uncertainty.
And Colin, this plot's showing all transitions, not just fire, right?
Right. Thank you.
And then just another useful thing people might find useful in the options is to show no data, like to not show no data 0, right? So the first year, because the first year isn't really a no fire year, it's just not being modeled.
So there's a couple ways we could do that. We could turn it off the way Leah said, or we could just model it like that. What was the other thing I was thinking of? Can't remember. Oh, proportion. We can also look at this as a proportion of the landscape, and we can see that we're on average burning about 1% of our landscape. But in any one year, it can be as high as 10% and as much as 0, obviously. So we brought in that variability. That was one of the questions. I think it was asking you about that. What do you notice about the variability across iterations for your area of burn? This is what you should see. Got quite a bit now. And then it asked you also what was the effect of the large area burned in 1998. That was on the historical run. So if we went back to the historical run and took these all off, and just looked at the historic fire, where we saw a big spike in 98, just to answer that question. If we look at a plot of the 3 states over time, we see that in 98, there's this big jump in deciduous forest, which we'd expect with a lot of area burn. That was the answer to that question. At the very end then, it asked also if we introduce this variability now, what's the effect? We've looked so far at the effect on uncertainty in fire. we can also look at the uncertainty. It asked an old conifer. So what I can do is take this scenario off the results set. So let's look again at the baseline fire probability with no variability, add that to results. And I will also look at the 100 Monte Carlo. Well, actually, let's look at the 6, the one you guys probably would have had. So this is just comparing the two with the extra variability. What's the difference in old conifer? So again, just to reiterate how we do this with the charts, state classes, we can look at the area. And in this case, we don't need to disaggregate by anything because we can just filter for only conifer and only age 80 plus. So that's this. And so here we see the two means, which again, we expect this is the mean conifer, old conifer area. If I turn on the variability, we can see that there's no variability when I don't have any in the model, but when I introduce the transition multipliers, I get this representation of the variability, and you can see that it's increasing. Now, once again, you're seeing some sort of odd behavior in the projection of uncertainty because I'm only running 6 Monte Carlos. If I up that to 100 Monte Carlos, that kind of smooths out a bit more. Let me just take off the one with 6. So this is kind of the expected uncertainty we see. And again, now we haven't really talked about how we measure uncertainty. And what I'm showing you here is the envelope that represents the full range of my 100 Monte Carlos. That's what this min and max is. But often we try to eliminate the effect of running a certain number of Monte Carlos in our representation of uncertainty. So we commonly use percentiles, or we call them Monte Carlo confidence intervals. And so the one that we most often use, like a lot of statistics, is what we call the 95% Monte Carlo confidence interval, which is the range between 2.5 and 97.5 percentiles. Okay, so if I do that, this is, it doesn't let me do it for one of them. And this is the challenge now. When I only ran 6 Monte Carlos, I don't have enough Monte Carlos to establish the 95% confidence interval. In fact, the software is telling me that with only 6 Monte Carlos, the best I can do, with all 6 of them, the full range only represents between 15 and 85%. So that's the 70% confidence interval. So again, this is a reason to run more Monte Carlos. If you do the math, it turns out if you run 40 Monte Carlos, you can just barely establish the 95% confidence interval. So let me just actually remove all these and only look at the one with 100 Monte Carlos, add it back in. And now it will allow me to go 2.5 to 97.5. Okay. And look at this is what we would call the 95% Monte Carlo confidence interval around the mean projected old conifer area. And you can see the uncertainty increases as you get out in time. It's bigger here, further out into the future, based on the way the modeling works. Any questions about that? Last thing was it just asked you to look at the spatial pattern of projected fire. So let's take a quick look at the maps. So again, we could create a map from scratch if we wanted. And we could look at 2014, I think, to 2033. And we could look at just fire here for one of the iterations anyway. And so what you were meant to observe is, first of all, the total amount of fire. Like there's quite a bit of fire on the landscape here, none in the next year. We go across, we see quite a bit of interannual variability in fire. And again, that's what we expect. We've modeled that variability in time, but we haven't done anything to represent the variability in space well. So what you're seeing is this speckled pattern where the cells that are being selected to be burned by the model in this exercise are all being selected independently and randomly. And so this creates a unrealistic, obviously, pattern of spatial fire in the landscape. We're only halfway there. So that's what the next exercise will do, is start. We already did a little bit of that earlier, but we'll talk about how to do that using spatial multipliers in the next exercise to solve this kind of conundrum. The bonus question, just to show you, this was very similar to the bonus that we worked on a couple of exercises ago. It's a little bit tricky. We were doing it before with targets, actually shifting the targets up and down. What we did in this simulation, asked you to do here, is to create the block pattern of harvest using multipliers instead of doing it in the targets. So we set our target for area harvested to be 2,000 acres per year. We set it once here, and now we asked you to go over to the multipliers and add some multipliers in here to scale the targets up and down. So that's just to point out, first of all, that when you apply multipliers, they apply to both probabilities and to targets, anything to do with a transition. So they can apply in both ways. And so here we're using the multipliers. We could in here scale the fire up and down, actually. But here's the section where we do the harvesting. So we went through this last time. I won't go over it too much. But in the first year of the simulation, we set a multiplier of 1 to tell it to direct, all of that. So it's including block A only, and it's accepting its full allocation of target. And we're setting a multiplier in the other blocks of 0 to shut them off. So the model says, okay, here's how much available area there is in time step in 2014. It only finds area available in block A because the multipliers are all set here to 0, and then throws all the harvest at that block. And then in 2018, similar to what I showed you yesterday, we turn off the harvest in block A, turn on a multiplier of 1 in block B, and the other 4 blocks maintain their value of 0 going forward, and so on. So if we do that, we get something that looks like this. If I look at the output, this is the pattern of harvest across the landscape. Whoop, that's the maps. Sorry, I'm in the wrong screen. If I look at harvest by block, again, to show you how I do that, I create a chart. Harvest is a transition. The total area, I could disaggregate, but I don't have to here because I'm only going to include harvest by, I only want that included, and I want it for all the blocks. I don't need the blanks. I think that should do it. Oops. I have to disaggregate by the harvest blocks. And they're all 0. What is that? What did I do?
This is the no harvest scenario, Colin.
Ah, thank you. I got the wrong scenario on here. So that was a good check that I had no harvest. And so this is what you expect. It's, again, we can turn off 2013 because the transitions only start really in 14. And so we get harvest of 2,000 acres happening for 4 years, and it shuts off, moves over to block B, block C, block D, block E. So it's moved the pattern around. And anyway, you get the idea. You can use these multipliers in various ways to vary targets and probabilities. So any questions about what we did there? You know, a key other point that we just kind of brought up in this exercise is that you can characterize many inputs in the model by distributions, just about all of them. We characterize the multipliers for fire. We sampled from a distribution, but you can bring in distributions for anything. Bring in your own custom distributions. There's some built-in distributions and sample from them. Just to give you an example, if I look at the Hawaii model that we were looking at before, if I just look at how we use distributions in this model, let's go down, where's distributions? Actually, I'm on this is quite actually this is a complicated, more advanced feature. What we've done in this, if we look at the distributions here, I don't know if I want to get into this, but what we've done here is we've actually created covariance between the distributions that we're sampling from. So this is a very advanced feature where what we've done is we've brought in what we call an external variable. We actually have, if we look at this external variable, what we're doing is we created up this variable called the historical year that we want to sample from, and we're sampling a value between 2002 and 2011. So this is a simulation where we have a historical record of fire data between 2002 and 2011, and every future year in our simulation we want to pick one of those 10 years and say use the fire probabilities that I observed in that year, but use them as a set. You know, I have probabilities for different types of fire, and I want them all to be, because they covary together, a high fire year is a high fire year of all types of fire and a low fire year. So to create this covariance, we set up this, we call external variable, that just samples a historical year for every iteration and time step of my simulation. And then based on the year, that it gets sampled, if I go over to, where was the distribution? Here, if I look in this table here, for example, let's just put this out to Excel. If I put this out, let's just look at, say, the fire probability I have for forests, and this varies by moisture zone as well, so we won't concern ourselves too much for that. But what we said here is that in the dry moisture zone, historically in 2002 we observed this burn probability for forests. 2003 we observed this. 4, 5, 6, 7, and 8. So these are the actual values for proportion area of burn that were observed in each of these years. And what we've said in the model then is if you in the model sample for this external variable that we just showed you called the historical year, if we sample a 2002, then go and use this probability for forest. And similarly, if we go down to grassland, we will see that grassland has a value for 2002. So what this does is on a particular iteration of a Monte Carlo, it ensures that if we sample this value for forest probability burned, we'll match it with this value here for grassland and this value for shrubland and everything. So we maintain the covariance that was observed in the original data when we do our sampling. So a very advanced feature bringing covariance.
Colin, can I add something?
Yeah.
The temporal multiplier, the transition multiplier distribution and external variables is how my projects introduce climate change. So this is advanced, but if you want to do climate change, this may be one of the ways by which you do it, because our external variables are the, that was one row in Colin's thing. I bring in standard precipitation and evaporation index time series over 100 years replicated with a stochastic weather generator, and I bring that in the external variable menu, the distribution menu reads all the same time series, but they're correlated. They all read from the same time series. So, and this is how the climate change affects fire, drought, flooding, and whatever you want. But they all read the same value. So a dry year for fire, so let's say it's dry, it's more likely to burn in your forests. Well, that will match up with a dry year that affects your flood regimes. And it will, and if there's insects that are tied to dry conditions, and same thing for wet conditions, then they're all correlated. And then that reads into the transition multiplier menu where it affects the probabilities in the model. So these three menus are really important for climate change. And you just don't look at them the first time and figure them out unless you're a genius, but it's just to warn you, these are important menus.
Yeah, Stephen.
So can I just ask there, so the covariance or the correlation, that has been informed by the data itself in that case, is that right?
Yeah, that's what we're doing. So that's the way we bring in covariance, is we do it empirically, right? We just look at the actual data and don't try and represent it using any kind of statistical fitting. It's done strictly based on whatever the data shows. Yeah.
So is there a capacity to not, if you're not reading in like climate temporal data, that you want to impose some variability for two particular aspects of a transition, to impose a degree of correlation between those random variates?
Yeah, so in the limit, this feature that we're showing you here with all the distributions and external variables got added maybe 3 or 4 years ago, Louis, probably. And prior to that, there's another way to express variability in the model that we haven't really looked at. Actually, I think I have an example. I'll show you this. And it's far more, you'll see that you open the door to full flexibility, but with it comes enormous sort of data management requirements. And that's why we use these distributions so often. But I'll just show you an example. I think I have one here this is the Trout Lake Forest. This is the parallel to the thing you've been working in the exercise. So let me see. I think I was looking at it before the exercise. So I think in here, if I go to the multipliers, yeah, this is an example. Let's look at this just for a second. This isn't going to answer I mean, the shorter answer is, Stephen, yes, you can represent ultimately any kind of covariance you want. Whoops. But you'll see that it can be quite a big lift to do it. So in the limit, there's just every input in the software has a column called iteration. That's an optional column. And basically what that column does is allows you to provide the actual inputs that you want the model to sample from for a particular variable on a particular iteration and time step. So it's kind of, you can force it to put whatever probability you want in there on that iteration for that variable by explicitly specifying it in the input, right? And this is what, when I set up this file for this particular model, I did it prior to this distribution feature being there, and this is the only way to do it. So just to give you an idea, actually, no, I don't have iterations in here. Shoot, where do I have them? Are they in there for certain variables? Oh yeah, they are for some. Okay, let's find one that's done that way. Yeah, so fire variability. So this is an example where iteration 1, let's just say on time step 1, I've told it that I've gone and externally, before the program started running in STSIM, I went and gave it the distribution sampled of all the fire values And I created that in an R script and then loaded it in for all 100 Monte Carlos. So I created the sampling regime myself. So if I wanted to create some other kind of covariance between two inputs, I could have created this fire variability time series and some other input that I wanted to covary statistically however you like, and give them the STSIM with the fully specified series of values that's to use on every iteration, and the covariance that you intended there to be there will be replicated in the simulation. But you end up with these very large files where you've had to pre-sample and pre-generate the covariance through the specification of all the values by iteration.